All right, we're getting into cylindrical geometry. So let's see. Let's assume we have a pipe. Let's see if I can draw this well. Let's draw a pipe. I'm trying way too harder now. Something like this. It's a pretty cracked pipe. Is that what a pipe looks like? Yeah, sure. Alright, and then like this. And then this will be open. Alright. Let's say we have our pipe, and let's call this, let's call this material stainless steel. And let's define a thermal conductivity for stainless steel, which we're going to call 15. And that's, we know the units on there is watts per meter Kelvin. Okay, and within our pipe, we have fluid flowing on both sides, on the inside and on the outside. And there is going to be, yeah, there's going to be a H. Yeah, okay. So we've fluid flowing on both sides, and the H is going to be different for each. So we have an H naught, or we'll call it H1. We have H1 and H naught. We also have a T naught and T1. We know the length. Define a length. And we know the radiuses. So there's like a radius here, and then there's a radius here. Okay. So let's write all these values down. The radius of the inside, the interior radius, that value, outer, it's just a little bit bigger. Inside temperature is 130 degrees Celsius. G1 is going to be 65 degrees Celsius. Right away, we know we're going to need it later, so I'm just going to define our temperature drop. 65 degrees Celsius. Let's get our H's. And that's watts per meter squared per Kelvin. Okay. And it's a little bit higher on the inside. Okay. We got all of our values down. There's a lot of values. One thing to note is that, not that it really matters. Actually, I'm not even going to make a point that it doesn't matter. I was going to say this T naught is the temperature of the surface, but it doesn't really matter because we're using this H. Just ignore what I just said. Okay. Alright, so let's say we want to find the heat transfer at the surface. So, question from me. Within a cylindrical geometry, is Q constant at all radial places? So this is the cross section. Is Q constant as you move out? And yes, Q is constant. Capital Q is constant. Let's write this, is not a function of R. It's not a function of R. What is, on the other hand, is heat flux. Heat flux is a function of R. So heat flux, as your surface gets larger, your heat flux is going to get smaller because you can dissipate on this outer surface. You can dissipate more. You more area to dissipate the same amount of heat on. So your heat per unit area goes down, if that makes sense. So the reason I'm making a point of this is, as I mentioned in the topic video, if you watched that, is that you're going to want to define these problems in terms of Q. So basically, let me just write this. Q equals UA delta T. This is the equation we're going to want to use for these problems. The reason I'm not writing it as something like Q equals U delta T is because this gets a little ambiguous because now your Q depends on where you're defining your R to be and which surface are you looking at. So this Q would depend on whether we're picking to look at this surface or this surface, and it's just a little, for me, I don't like it. So always use the total heat flux, in my opinion. Okay, so now let's solve for UA. So UA, I'm gonna call one term, and we're gonna write this as 1 over the length 2 pi. So this is the inner surface, and we're losing heat H naught. Okay, so those are our convective losses. These are our convective losses at the two surfaces. And then we also have from within the stainless steel pipe. If you want to see where these equations come from, watch the topic video. We got the stainless steel. There we go. Okay. So this is going to be our equation for the total resistance of our overall heat transfer coefficient for the pipe. Okay. If we solve these now, do I really want to plug all this in? Yeah, sure, might as well. Yeah. All right. All right, so if you evaluate the terms, and also I apologize, in my original formula I forgot to write the L for that one. But if you evaluate out these terms, these are the three numbers you get. So summing those, we're going to get that the 1 over UA is equal to this value. And so now our overall heat transfer coefficient times our area is going to be 98.2. So now we can plug this back into this equation. So our total heat transfer at any area is going to be equal to UA delta T, which we know UA is 98.2. And then delta T is 65. And so our Q is going to be equal to 6,385.5 watts. And that's in SI units because everything in the above was in SI units.
Okay, problem 10.4. To increase the heat dissipation from a 3 centimeter outer diameter tube, circumferential fins made of aluminum are soldered to the outer surface. So, we have a tube, and we're soldering on larger fins. I don't want to draw this like something like this. Kind of. You get the gist. Okay. So we have this fin on here, and they are very thin. They're 0.1 centimeter thick, or 0.001 meters. They have an outer diameter of 6 centimeters, or 0.06 meters. The surface temperature is 100 degrees. And we're going to assume that's constant throughout all of this. Pink sticks out more. So all of this temperature is 100 degrees Celsius. And the environmental temperature is 25 degrees Celsius. There's a heat transfer coefficient of H equal to 65. Calculate the heat loss from a fin. So, generally, the way we want to calculate heat loss for this fin is we're going to use Fourier's law again. So we're going to have the heat transfer coefficient. Since we're not looking at the through this law, we have the temperature at the surface. So we're just looking at the temperature like from the surface into the ambient. So we only have H here. We don't need to do an overall heat transfer coefficient. So we're going to have H. We're going to have the area, and then we're going to have delta T. Now, for these fin problems, generally, to make them simpler, we're just using efficiency. So I'm going to redefine my area to be area effective. I could just throw our efficiency out as a coefficient in the heat flux, but for the other problems that are not circumferential fins, it'll make a little more sense to do it this way. So for consistency, I'm going to define this area effective to be the area that's losing heat of my original thing. So in our case, this would be the heat loss like from the inner pipe. Now, in our case, the circumferential fin is completely covering it. So this is actually 0. But then we have the heat loss from the fin, from the surface of the fin. Now this might be less effective than losing heat directly from the surface. So I'm going to add in an efficiency, so a coefficient to like force our solution to be right. So when you're doing these calculations, you're like assuming that when we make this delta T, I'm going to use the temperature at this surface. And we're basically assuming that, it's constant all throughout, which is not actually the case. It's probably colder in the fin. But to counteract for that, we're just going to introduce this efficiency, which is just going to become a coefficient. And that can kind of fix our problem. Generally, you can mathematically derive the efficiency like as a function of geometry and stuff. But I'm not going to do that because it's out of the scope for this. So for us, we're just going to assume it to be 0.88. And let's go ahead and calculate this. So that's going to make our effective area 0.88 times, let me move this down, times the heat loss we're losing from both, God, this is getting ugly, from both sides of like this surface. So we have two surfaces there. So it's going to be times 2. Here, let me do a little mini graph. So we have the rod, and then we have like a bigger rod inside. So if we want to calculate the heat loss at these surfaces, we need to take the larger circle cross-section, and then subtract the inner cross-section. So How are we going to do that? That's going to be, we know the area of a circle is pi r squared. So pi, the radius of this bigger one, the one I labeled purple there, is, what did we say that was? That was 0.06. And we're going to square that, because that's our radius. And now we want to subtract off the smaller ring. So that's going to be pi. And I think that was, what did we say the smaller one was? 0.03 centimeters? It's 3 centimeters. So this is 3 centimeters, or 0.03 meters. It's important to keep everything in SI units, so it works out. It's just easier. So this is like the exposed area, right? Okay, so let's calculate our effective area, 0.06 squared, and then we can essentially just subtract off 0.03 squared times pi. We have two surfaces, so we times by 2, times our efficiency. Area effective is going to be equal to 0.0149. Let's plug this into Fourier's law, which we wrote above. H, they said, was 65. 0.0149. Temperature difference is 75 degrees Celsius or Kelvin. So times 75 times 65. And I went wrong somewhere. What the heck did I do wrong? Oh, okay, I see where I went wrong. I took the outer diameters. Okay, so this, I read it wrong. This is, the 6 centimeter was the outer diameter, so the radius was actually 0.03 meters, and for this one it'd be 0.015 meters. Oopsie doopsie. So this comes 0.03, this comes 0.15. That's going to change, that's going to change. Okay, let's do this new calculation. 0.03 squared times pi minus pi times 0.015 squared times 2 times 0.88. Okay. Plug this in. We're going to go ahead and get a Q of about 18 watts, which is what we're looking for. So there's a circumferential fin problem.